Good morning, everybody. It's not the first time I had the pleasure to speak before this audience. Okay, before this audience. Today I will speak about one little topic of my whole theory. This is the examples of iron 26 isotopes, how they have acquired the atomic nuclei binding energy. Yeah. So several authors predict that alpha particle structures could be present in atomic nuclei. There are convincing arguments of such structure, and I am of that opinion. So for me, to calculate the binding energy of the several nuclei, there is a first point to consider. This concerns this alpha particle binding energy and its relationship with those of deuterium, tritium, helium-3, which are nuclei pre-existing that one of helium-4, actually. So a second point I consider is to see if these three binding energies play a role in the bonds between the alpha particles binding a nucleon of an alpha particle to a nucleon of another second particle. For more detail, please refer on my poster presentation. I have two poster presentations, one devoted to the general theory and the other on iron I will now present. So according to my theory, the nuclei of the various elements are constituted with alpha particles and other nucleons grouped in order to create subnuclei linked by four types of bonds. I have called for facility NN, NP, NNP, NNP. The binding energies of deuterium, which is NP, tritium, NNP, helium-3, NPP, and NN are linked through the following equations. So for more details, please refer to my poster presentation where it will be shown that the hypothesis of the structure of the N-alpha nuclei can indeed describe the binding energy systematics. In such approach, the system in its ground state behaves like a crystal with stationary configuration and shape and with defined bond values between the various particles. So according to my hypothesis to my theory, the binding energy of every nucleus is the sum of the binding energy of its different substructures and the binding energy among these substructures. The examples presented today are the various isotopes of iron. There is also a poster representing the same issue. The values used for the calculation of the binding energy are the following. So you can see these values. And you can also see the value of the line. I can explain you later what it is. The NN and NP are the most used bonds. Generally, they oscillate to form an A bond, what I call an A bond, equal to NN2 plus NP2. And we can say that the NN value is comparable to the mass of quark down, and the NP value comparable to the mass to the quark up. If you add both, you see you come to, in my theory, to 7 MeV.16, and in the general theory, 7.2. So it's quite close. So there is something with the quarks in my theory, but there is something a little bit more I will explain later. The binding energy of alpha and NN are defined in the documents on internet. This is my theory. If some are interested, you can just look at this website. Philippe, like in French, so you have to do the right typing. Also, the definition of the lines and the relationships with their values in MeV is given. And you can also see it in the poster presentation. The basic rule for determining the nuclei binding energy, actually there are three. For the lowest one, let's say, the rule is binding energy of N is X alpha plus X BNN 2 plus NP2. And if they are supermean neutron, Y, EB, and N plus NP. The basic rule we will I will now illustrate is the case for iron. It's a little bit different. It's X binding energy alpha plus X plus Y binding energy NN plus NP. But there are also some little deviations. NN and NP could be replaced by tritium or by helium-3 binding energies. And the rule for the heaviest one is a little bit different. As Edo, as Lin said, there is a problem. I have solved it in a certain way. It's difficult to explain now, so I will skip. Voilà. 2 remarks. Geometrical structure of atomic nuclei. So in my theory, the binding energy of the nuclei has an unidimensional value broken down by these value I just explained, binding energy of alpha, NN, NP, NNP, NPP. My work is not addressing the 3-dimensional model of nuclei in the sense that I'm not looking for a structure of these nuclei, but rather for the distribution of binding energy within them. So the structure is led to others with whom I work or I wish to work. Nevertheless, my work could be complementary to those dealing with this topic. A comparison with 3D nucleic models could be relevant. And second remark, which is important for LNR, it's important to know the distribution of the binding energy in each element or isotopes at the beginning and at the end of the LNR reaction in order to follow that process. So this we will see for iron now. So I have taken several isotopes for iron. First one, 5226, as you see in the left. The last one is 61. So these are those which are considered the most important in the literature. So you can see here, where should I point? Here, that there is no neutron supplementary, only alpha particles, because it's 5226, you see, so we have, let's say, 26 proton and 26 neutron. The alpha particle here are bound by A bonds, which are, I recall, NN divided by 2 plus NP divided by 2. The core is unstable because there are only NP values. The NN value is lacking. Why? Because all the locations are occupied. We have 26 locations, 13 between the 13 alpha, and 13 between the cross. So it's always the same. It's in my theory, you have one direct link between the alpha and one cross link. And there, if there are 13 alpha, there are 13 direct and 13 cross. If we have neutron supplementary, we will see immediately what happens. So all the 26 locations are occupied. 13 are occupied in the ground with A. 13 in the core, but only 11 NP and 1 NNP, because this is equal to 2 lines. There is no N supplementary, and then there is a deficit of lines. I will explain you what it is exactly, of nearly 24 lines. This is 13 MEF, 3% of the binding energy. So this cannot be stable because of this deficit. In the calculation, there might be other physical explanation Lin gave or Edo gave, but for my calculation, you see. Now we have 53. 1 N is added. The 13 locations are occupied by some A bonds every other time. You can see I have A divided by 2. It's not enough. This yields instability in the nucleus. Some A bonds are missing 3. If you calculate, you should have 3 A bonds more in order this is stable. The deficit of line is 18 lines, roughly. This represents an increase of more or less 6 lines in comparison to iron 52 due to the presence of one N supplementary. Actually, I have noticed that the N supplementary acts as a sort of catalyst. It's not a catalyst, but a sort of catalyst in order to stabilize the nucleus. So the deficit is only 10 MEF instead of 13 MEFs before. It was 52. Now we come to 54, which you see is stable. Natural abundance 5.8%. We have 2 N supplementary. You will see that here in the ground there are only A bonds. Also in the core, A bonds, except for here. Actually, we should add NP divided by 2 each time to have A bonds, to have a perfect system. But this is enough to make it stable. These 2 NP bonds which are missing to achieve the A bonding of the score are actually a sort offset of the system is offset because we have the N supplementary. As I told you, with the N supplementary, there is a possibility to stabilize the system. So we could imagine that there is an exchange of this 2A with the 2N, and then we have N, which is bound to the alpha with the NN bond, and we have 2 A's here, same here. Here there is a NPP because in the case of iron we have 13 alphas. This is an uneventy, of course. If you have 12 or 16, it's much better, but with 13 there is a little difficulty, but this is a detail. 55, this is not stable, but the lifetime is relatively long. Can you see it's more or less the same. Nevertheless, when you have 3N, it's less stable than if you have a pair number, how do you call that, 2 N's or 4 N's, etc. So there's nothing special to say for that one. 56, of course, is the most abundant in the nature, 92%. You can see that there are 4 N supplementary. A everywhere, but with the exception of here, because of the uneventy of iron, because of the 13th alpha. So it's stable. The excess of line is 4 lines. There's a little excess, but this represents only 0.466% of the total binding energy, which is very few. So we can say that this is stable. 7, it's 57 now. We have also a stable nucleus. 2.1 natural abundance only. You can see here we have only A ones. Let's say, as I recall, quarks up and quarks down, because it is that. So, and the N are linked by NPP ones. The core is perfectly shaped. The 5 N supplementary are bound by particles with 5 NPP bonds. So there is 5 lines in excess because 5 NPP minus 10A is 5 lines, or let's say 2.7 MEF, or 0.556% of the total binding energy. So all this is calculated after after that, this is the value of the literature. This is my calculation. 4 kf difference. This is, if I have time, this is a tentative of structure. You can see how it is. It could be structured as a crystal. It's not very interesting because my drawing are not very good, as they're not in 3D, etc. It's not my talent, so I just skip it because of time. Same for 56. You can see that for 54, the n were here. For 56, the n are here. I have changed it a little bit, the figure. I have put NPP instead of A and put the A elsewhere. But basically, it is the same crystal. 57, the same. Now 58, this is stable, but the abundance is natural abundance is not very important. You can see always the same shape, the same diagram, with still here NPP, etc. But we have more NPP because we come to a zone of instability. So it's stable. Nevertheless, there is an excess of 10.18 lines. This is 5.666 MeV, or 1.11% of the total binding energy. The stability line is minus 1% plus 1%, more or less. The figure so shows the limit of the stability of the nucleus. There are many NPP bonds. 59. Here we have also a lifetime, you see. And you can see the core is less, how do you say that, less even than for the others. And there are many NPP. So this explains why it is not stable. There is an excess, 1% deviation, but the general structure is not quite good for 59. Also, because there are 7n. Generally, I said if you have a number, even number, it's better. 60. 60 is interesting. It's decaying, but it's a very long lifetime. There is an excess of 12 lines, or 6.7 MeV, you see. But compared, what is interesting, you can compare it to iron 56. We notice the same core structure. If you cannot remember, but I tell you, this is exactly the same. But in the case of 56, we had 4 Ns, which are linked by each time 2A bonds. In this case, we have NPP 8. So if you do the calculation, you will find exactly these differences. So this means that there is no manipulation of on my side, because I have taken the value of the literature. I take the two values, 56, 60, I do the difference, and the difference is that one. So there is not even nothing which is taken by myself, done by myself, sorry. So we have here a second figure. It's a bit different. I did it a little bit differently. We have the same core than for iron 57, if you remember, all A's. Of course, here we have NPPs and NNPs. So in the case of 57, we had 5 NPPs, if you remember. Here we have 5 NPPs and 3 NNP. So, and this is, you can do the calculation, you will see exactly the difference also. For 61, maybe it's all it is the same, as there is 5 minutes remaining. I'll stop here, and I'm ready for questions. Thank you.
Philippe, well, my point is that I really need a 3D model of your...
You need...
I need a 3D three-dimensional model of your atom. Otherwise,
Yeah.
it's very confusing to me, you know. Maybe it's correct, but we need a 3D model.
No, you are quite right. I tell you, I am only dealing with the calculation of the binding energy, which is a unidimensional system. I need, of course, the help of some others dealing with 3D. But you can see that there are so many coincidences that there must be something. And even if I took my work away, you can see that in case of ions 56 and 57, they're practically the same than the 60, iron 60. And this is just done by the calculation of the literature. So there must be something. It's not me, but I agree that my work, let's say, is a bit deficient on that point. I'm working alone. I am not backed up by a university, not backed up by nobody, so it's difficult to do everything alone. So now I have calculated all of them till atomic number 43. I have done some more because of some interest of somebody. I will show later. But of course, I have my limits. This is the point. Please.
So, thank you, Philip. This is, as you say, there is something in it. But I was looking during your presentation at the deficit of energy. It seems there is not a direct relationship between this deficit and the stability on the lifetime. At times it's stable,
Absolutely.
it shouldn't. The next one is less deficit, but it's not stable and so forth.
This I wanted actually to develop, but I have not much time. Actually, it's absolutely true, it's a very good remark. There is, of course, a relationship. Those which are the closest of my rule, maybe I could show. You see, here you have, for instance, the structure. We have here iron 56, you have the calculation, and you have the difference with the basic rule. You can see. So when it's beta decay, beta minus, it's plus. When it's beta plus or EC, it's minus, generally. There are some exceptions. Of course, it's also a problem of the numbers of n supplementary. I told you if there are even numbers, it's easier with 2, 4, etc. And the exceptions are only 5, 7, 9, and normally they are not stable because of the number of neutrons. So this is a problem of the structure. I should discuss with those dealing with structure. Yeah,
Thank you, Philip. I was wondering if you could show the difference between iron 55, which decays to manganese 55, or
yes,
iron 55 to manganese 55.
Of course, I have it in my library, but I haven't it here on my stick. Sorry, but I show you later.
Okay, because it would be interesting to
I'll
perhaps show
later.
the people the difference between those two.
Yeah, as I said, I calculated all the elements plus all the isotopes, the major one. 20, 25 maximum binding energy, and it corresponds to what I've shown here. So there are so many occurrences, so many coincidences that there is something. Of course, there are limitations in my work. I fully agree. It's the reason why, if somebody is interested to work with me, or I'm interested with work with them, we could work together, but it's difficult because we're not located at the same places, of course. Ideally, we should be hired by university 6 months or 1 year to finalize the work, but this is ideal.